You know, as you notice that the call has begun, but I think we should start because we don't have a lot of time. Last week we missed our session, so we're going to have to restart from where we stopped. I remember that the last topic we covered was efficiency tricks for training neural networks. Just give me a moment to share my screen, please. I'm just going to share. Please let me know when you can see my screen, everyone.
We can.
Yes,
Okay.
yes, we can, yeah.
Okay, so I'm just going to, how do I carry this away? Okay, just move it to the bottom. And yeah, so we dealt with efficiency tricks for neural nets. And I think that we did not do the code walkthrough. And a big part of why we didn't do that was a lot of people had not had time to cover the videos. So we felt it was more beneficial to spend time, talking through the slides. And I remember that Charles led us that particular day. And Charles is here again. Hello, Charles. So I thought we might do that code walkthrough today, together as a group. There's only one PyTorch. There's only one PyTorch script. They didn't translate the rest of the code from Dynet, which they use. So we'll be looking at skipgram. Specifically, we are looking at negative sampling, how it's employed as an efficiency trick for training a word embedding neural network. I thought we might start by watching a small section of the, or maybe the slide. Maybe the slide probably be better than the whole section. All right, so from now on, I'm going to try and get more people to join us and interact. And so let's start with, I think Charles led that day. So Charles, if you can remind us you can remind us about the discussion about softmax and how expensive it is. Can you share something?
I'm sorry, I didn't really get what you said.
I said if you could share something about softmax and the reason for, why we might need to think about efficiency when working with softmax.
Okay, yeah. So if I remember correctly, I think the reason why we consider efficiency actually softmax is one of like the most computationally expensive operation to do, and actually we were able to establish the fact that it was expensive because of this denominator that we have here, right? So if you have to do this operation for every of the words or for every of the feature rather, it's very expensive. So there was a trick that was actually covered in this slide that helped us in making softmax kind of less expensive. Yeah.
Okay. Yeah, so I think Charles has covered it all. We mentioned that the softmax is expensive because of the denominator. And an intuitive way to think of the denominator is that I think there's a particular diagram here that helps. Is that you want to find probabilities over the entire, for the case we are doing language modeling, you can say over the entire vocabulary. And for context, some language models have very large vocabulary. GPT-2, for example, has 50,257 tokens in its dictionary. I know some are smaller. I think Google Mini has one is smaller, maybe about 9,000 or 5,000. But you can imagine that for 50,257, that's a very wide tensor over which you need to take calculate your softmax to output probabilities. So if there is a way that you can handle that operation, it's in your better interest because GPUs often have limited memory. And so in that particular week, I think they mentioned a number of ways by which this can be done. There's importance sampling, there's nice contrastive sampling, there's simple negative sampling. Simple negative sampling is used in the work of Mikolov et al. That's where they train What2Vec. What2Vec helps you to get embeddings for words and allows us to draw out relationship like if I'm correct, I think was it king minus man plus woman to give us queen or something, to map your words into, what do I call it? So that's into a computational space where you can begin to draw relationships between them, and uses a neural network. And so in the work of Miklo et al., they employ simple negative sampling to replace the traditional softmax separation. So the code walkthrough that we look at that we're looking at looks at the skip gram model and demonstrates the way that negative sampling is employed there. And yeah, as usual, you can find the code on the GitHub. But I have a local copy here, which we are going to try and look through together. I myself haven't had time to look through it, to be honest. I had it open for like an hour before the meeting, but I couldn't get through it completely. All right, let me just create a new file and let's call it skip negative sampling.ip ynb and split right. Please feel free to chime in, contribute as we go along. So I know, everyone is being carried along. I think we covered some of this last time, specifically the part that reads the data. I hope I'm working in the right environment. Let me see if it works. I don't know. What environment do I use? TCCTP address. I need the one that has. Let's just see if this guy has. It's a PyTorch environment. Okay, so I'm just going to say import touch. Okay, touch computer that is available. Actually, let's say no. Okay, correct. All right, so looks like we're in business. All right, so I'm just going to try and step through the code. We have the code on the left, but I feel sometimes like walking through it in Jupyter Notebook always helps. Okay, let's start with the data. Just going to create a section and say data. Let's convert this markdown. Okay. So we have a read data set function. Copy this too. What kind of that could do? Okay, so yeah, we'll find this. Okay. It's why. Okay. I think everybody remembers this Slack statement. It's if you remember that day we had to look through it together. It's an interesting statement that just maps each word that is passed into the dictionary to the the letter of dictionary at that particular time. And since we know that the dictionary has to have unique keys, it's just essentially mapping each word to a unique number for the vocabulary. So okay, let me start from the beginning then. I already imported the default dict now. Oh, okay. Now we're going to initialize it. And then we can read that data set. Okay, so let me just open the data file. Data, we're using which ones? PTB, train and test. Okay, so here's data for which you want to learn the word embeddings. There are sentences, and some of them are marked as unknown. So we have a function to read it in. Here. So you're reading the file. Split it, of course, into a list of words here. And then for each word there, okay. So they do a word count for it. Just count the number of times each particular word or token appears across all sentences in the corpus. And then for each line, you just see the representation of the line as numbers. So I think we can run this. Let's do this guy. So I guess we can. Let's call this. So we can say train is equals to list, read data set, and then slash ptp slash train.txt. So we have found or found. Oh, my directory structure different. Oh, okay, ptb, not ptd. Oh, okay, okay. I think we are good now. You can check to confirm that it was read appropriately. We indeed have a list. And what's that position? 0 in the list should be the representation of the first sentence. Yeah. So just where we said, this particular function converts each sentence into a list of tokens. You know, where the tokens, each token is a word, and the word have been mapped to a unique integer. All right. So we can do the same thing for the dev sets. Let me just Ctrl+C and then Ctrl+V like this. So now we have data for our dev, and then from there, all right, from there, check the number of words, and okay, and get a mapping for it. So what do we have? Y2W now. Yeah. So we can see a proper mapping now of what each word is mapped to. It's a reverse mapping in case we need to decode our sentences. So if you remember, first of all, we had our W2I in which each word is mapped to. Let me show W2I also. So we have W2I in which each word is mapped to, you see, a unique integer. But to help our decoding, we have a reverse dictionary that maps each integer back to a word. And they do that by reversing within this particular dictionary. So they unloaded the functionality to the order, but reversed the order of the keys and values to obtain this reverse mapping. And we can check number of words in our vocabulary and say there's 10,000 words. So that's something that frequently happens. I think that explains why we have unknown tokens in the data set. It must mean that there's been some form of pre-processing and that they've kept only the top 10,000 words probably, because that frequently happens. You want to limit size of the vocabulary. And then the rest of the rarer words are just mapped with this unknown token, which you see here, which is this unknown token we have here. Okay. So next we check how often these words occur. List X counts. Let me import number. Okay. Okay, the items. I have to close the list, then close the array. And you should be fine. Okay. And then so they normalize by, and then we can check counts again and see. Now the values are a bit different than before. So let's initialize the sort of probability, which we will probably update later on. Check that and see that it's just a complete list of zeros for everybody. So now let's update by saying check each word um, in word counts, which we created. Where is it again? Sorry. Yeah, which we created here. So for each word there, now we'll say update the word probability at that particular index. Word count, get the ID. Then divided by normalizing constant. Wait. So this part is a bit confusing for me. Does anybody understand this part here? Charles, Odun, am I still on the call?
Yes. Which one exactly?
This part where we are normalizing. So if you see, we've checked the number of words that we have. We're ready our train and test set. And then at this point, we take the count of data and we normalize. I can't remember exactly why. So I don't know if you could help. Or somebody sent a message. Dot item. So use dot item to retrieve. Let's say, for example, if you have a tensor that contains a single element, use dot item to retrieve it as a scalar. So it helps sometimes when you're logging. Like if I did touch dot tensor, and let's say 0.9, right? I think we'd have this. So if you call dot item on that, you should retrieve only 0.9 if you see it. So does that explain that, Benjamin? Sorry, Charles, you're
Thank you.
Hi, Charles.
Oh, yeah, I can hear you. So are you talking about line 69 or line 73? Oh, sorry, line
69 down to 71, where we have that normalization going on.
Yeah, so the normalized constant is we want to be able to divide every word by, we want to be able to divide. So basically normalization is each word divided by the sum of the words, right? So if you have 1, 2, 3, 1, 2, 1, 2, 3, 4, 5, that the sum is what? Sum is like 15, right?
So you divide by that 15.
Yes, so each of the words divided by 15, right? So I mean each of the numbers itself divides by 15. So that's how you normalize, because in that case, I think it sums up to 1.
Okay, so Charles is exactly right. I that's why I was verifying what's in this word count dictionary. I think it's the way they wrote the code that makes it a little confusing. So here's what's happening. Word count dictionary, the key is a particular word, what has been mapped to, and the next number, that's the value in the dictionary. Sorry, I shouldn't say dictionary since it's okay. I should say dictionary actually. Like code dot items. And the value is the frequency of that word throughout the entire data set that we have. So going by this word count tells us that word number 2 occurred 11 times, word number 3 occurred 12 times, word number 4 occurred 8 times, right? And so what they did was the list, they converted this to a list. So we have list X for X in this particular dictionary. So it lists everybody here. And then they put that list in an array. And then they now take they now normalize what's it called, everybody by raising it to the power 3/4. And then from then you take the sum. So it's normally what you do is you take the sum normally just to find total frequency sort of, and then use that to normalize. But what they did instead was to first take a 3/4, raise everybody to power 3/4, before they then take the sum and then normalize. So if we go back here then, so for each word in word counts, update its count or frequency by take the particular word and then divide by normalizing constant. How does this error keep showing? Word probability. Setting an element, an array with a sequence. How does that keep showing? I already
Yeah, I
already
think it's
ran.
on line 69. Yeah.
I think maybe I didn't run them in order. Okay, yeah, I found it. It was here. I should have indexed it to take this guy before raising its power 3/4. All right, let me verify that that guy is appropriate count. Okay, perfect. So now we just take word probabilities, someone to normalizing constant. Now we should run this guy neatly. So for word in word count, update. All right, so now we have our updates. So we can call word probabilities. Let's just call the items and see what we have now. Oh. Yeah. So now we have them as a proper float numbers after they've been normalized by some of the accounts. So we read labels description. Hold on. What they define as okay. Labels of text. Labels location. Labels file. So here they just read reverse mapping back to to a file. Okay, so now we need to look at the model together now. So let's just come here and say model.
I have a question. And what
Yes.
the last chunk, what it's doing?
So if you remember that we said I to W was a reverse mapping.
Yes.
Sorry, hold on. I to it's a markdown of code. Python. Yes. Remember we said that I to W was a reverse mapping. So what this is simply taking is writing this reverse mapping back to what's it called, to file. So I should open it here so you can see. So you can see each one of the label back here.
Okay, it's transforming it back to the original shape, right?
So if you remember I to W, the first one W2I maps each word to a unique index, right? And we said I to W is not like a reverse, which maps each index to a particular word.
Okay.
So now if you now go back to this code, you see that this thing is being written in order. It says that for I in range n number of words, write the particular word that corresponds to that index. So in essence, like in this particular labels.txt, the word on line 1 is token number 1 in our vocabulary. The word on line 2 is token number 2.
Yes.
You understand? Token number 3. Yeah. So in essence, we have our labels here.
Okay.
So we know the position of each word in our dictionary. Let me just delete that. So now we have to look at the skipgram model itself, which they define here. Audrey, sorry, could you, I don't know, talk about skipgram, what we discussed that day, or anything you remember really, just share about skipgram model. Does anybody else want to share? Anybody? Just so
sorry, I was trying to unmute my mic.
Okay. Yeah, let's hear now.
Yeah, so skipgram is one of the Word2Vec methods of like building a word embedding. So word embeddings are like representations of words, like vector representations of words, where in a way they show similarity between words. So basically there are two common types. There's skipgram and there's SIBO. SIBO is the continuous bag of words. So the difference between the two is with skipgram, you are trying to predict the context words from like a center word. I don't know if I'm completely correct. And I think SIBO, you are trying to predict a center word given a set of context words. Is that correct?
Does anybody want to help us verify?
Okay, yeah, it is. So with skipgram, you have like a word, a center word, and then you are trying to learn a representation of that word using the words surrounding it. So you pick a particular word and then you try to predict the words that surround it, given a specific window. Then
Right.
with SIBO, you have a set of context words and you're trying to predict the center word. So yeah, that's skipgram.
Let's see if we can put this in context. Let me use, what sentence can we use? I went to the gym today. At the gym today. All right. So let me highlight her so we know what we're learning the context for. Yeah. So we have the sentence, I went to greet her at the gym today. So with skipgram, as Odu mentioned, we pick a window size on which we say, so if we pick a window size here, we would have, I imagine, let's say window size of 2. And we'd have this guy together, and then we'd have, let's pick 3, just so we can have an interesting word on that size. And then we'd have these guys. Sorry. No, it's hard to tell them apart. But like, yeah. So we'd have, we're trying to predict her. We have went to greet to the left, and we have at the gym to the right. And both of them form, context for the word her, for which we're trying to learn the representation. And I think that should be our that should be a skipgram, right, Odun?
Yes, that's correct.
Yeah. And then for continuous bag of words, when we pick a window size, we have when to greet. And based on when to greet, I believe we're learning representation for her, right?
Yeah.
Okay. So today we're looking at skipgram. And as usual, when you're building a PyTorch model, you're building a model in PyTorch, you start by subclassing the touch.nn.module, and then you define parameters that your model takes. In this case, we have number of words, and we have an embedding size. And if you remember, we discussed something about an embedding size being I think we talked about tunable parameter, because different models use different embedding size, and it's often let's say parameter for classification of model, as whether it's a large one or a smaller one. So yeah, I think we've encountered the embedding module also before, so we use it here to initialize an embedding, and this is pass is equal to true. And then if you remember, I think we also discussed initializations. Did we discuss initializations? I think it was like 2 weeks ago or so, where we discussed the different ways you can initialize context embedding as equals to touch embedding number of words, embedding size passes equals to true once again. And then initialize this particular layer, okay.
Yeah, I think you made a mistake with nn.embedding.
Oh, okay. I keep putting underscore before words. I'm used to it. It's because they're separating 2 different words. I mean, they're joining 2 different words together. I always use an underscore to separate them.
Actually, mean the line above the line you are writing now is to be touch.nn.embedding.
Oh, I see. Sorry. You know what? Let me import from touch import nn so I don't have this trouble. All right, now I should have flexibility to just say nn.embedding. That's It's much easier to type. Okay, so we initialize the weight also. Oh yeah, just give me a moment. Let's check this their useful reference, which is listed in the code. Let me see if I can share this. Can somebody open this on their end? See if it offers anything interesting to us as we work. So then we define the forward function. The forward function which controls the forward pass of the model during training. And we have context, positions. Well, we don't have a lot of time at all. We have negative sampling. Negative sampling is called false. We say embed word is equals to, first of all, pass next one is embed the word the context then, and then we pass in context positions, and then we have a score. So yeah, so we see two things here now. If you remember, if you look at the init function, we initialize two different embeddings, one for the word and one for the context. So when we get to the forward pass of the model also, we use the word embedding for the word and the context embedding for the context. From what I see here, it looks like the model, the forward pass is just going to take the words we've mapped to index. So the word, they create an embedding for that for both the context and each particular word we are looking at. And then we take the maximum of the embedding context and embedding word, which we transpose first.
So do you average both embeddings at the end, or you just add them together?
The third word.
So do you average both the word and the context embeddings at the end, or you average them?
So that's something that I thought we might discuss again. I'm coming, sorry. Because what I saw was I couldn't have, I think the interpretation I had in my head is not eventually what I saw when I looked at the code today. So they calculate a matrix multiplication of the embedding context and a transpose of the embedding word. So now they say if you are doing negative sampling, they say that the score should be equals to -1 times score. So effectively, if it's 2, we just turn it to -2 as an example. Anyway, and then we just have otherwise, anyway, or after that, we have touch.sum. I didn't import functional. Oh. Okay. Let's go back here. And then let's take f.log sigmoid as the activation function. And then we pass in the score that we have. And then they return that particular object. Yeah. So this is what I found interesting is that there wasn't specifically adding like Odru asked about. I see it just looks like how do I explain it? Whatever the score is, in the case where you are doing negative sampling, that's telling the model that you know what this is the wrong word. You do that by this particular point where you make the score negative. So I'm guessing the more negative the score is, the more the model gets sure, like no, this is not a context word or something like that. So there's sort of like punishment for it. I guess the best way to run it to see. Is there any error? Object I to W is not defined. What does that mean? Anyway, let me delete this guy and see if we can run this model now. Object. No, there's no error now. There's no error. Okay, so let's have if there's any error with that. Embedding size, they chose 128. Somewhere to keep the embedding location. And then from there, initialize an optimizer. So we say optimizer is equal to touch dot optim dot sgg model dot parameters. I need to initialize the model then. So we initialize the model by calling it model embedding skip, passing n words and passing our embedding size, which we've defined. Oh, I didn't run it. Okay, so we defined it. Oh, there was no S behind it. It's what embedding. Where is it? Okay, yes, here. What embedding. Okay. Touch.init. Just there is no touch.nn.init. Stressing. Oh, come on. Okay. This time, yourself. Okay, awesome. So we have optimizer, and then passing our model parameters into the optimizer, and a learning rate 0.1. Define a general type to be used, and then there's no CUDA. My laptop doesn't have, unfortunately. Let me see if use CUDA. There's probably no point for this. Okay, so now a loss function. So we have a model, we have an optimizer. So the last thing really is the loss function to help us decide how we are going to optimize. So we have a sampling for negative words. So what they do here is they call np.random.choice. So we say, and then we pick the size, which you sample times k times length of that particular sentence. I think we should look at n and k again. I'm not sure they defined ahead somewhere. All right, I remember that. Sorry, n is equal to. Remember what k is. So we have n is 2, which is our window size. We have window size, and we have a k, and k is 3, which is number of negative samples to take. Please give me a moment. Hello, Yam. I just came to a meeting. All right, sorry everyone. All right, so we have number of negative samples to take. All right, so n is window size, like we mentioned I've deleted it. There's number of words to each side of the particular word we are embedding. And k is number of negative samples to take. Yeah. So the first thing they do in calculation of loss is to actually do our actual negative sampling. And here we have, so we have 2 times n, which is window size, times k, which is negative samples, times length of the sentence. So this means that if you had, for example, a sentence that contains 9 words, we're going to sample 9 times 2 times window size is 2, and number of examples is 3. So what's happening here is, let's say I am a good boy. And if we are choosing A as the word that we're trying to learn embedding for, then for good, we'll do a sample of 3. Let's get 3 words for good, 3 negative samples for good, 2 negative samples for boy, 2 negative samples for 3 negative samples for I. So that's why we have, so the first, the 2 shows that I'm multiplying for, and then you're sampling for both sides of the window. I think n should be window, then k is number of examples that you're taking, and then for each word in the particular sentence. So they do the actual negative sampling, then initialize an empty list of losses, and then we say for each word in the particular sentence, let's find positive words is equals to sentence x. If x is greater than or is equals to 0, else S. I think we define S upward somewhere. S is, I think, the unknown token. Where is it? S is position of beginning word. Yeah. Let me check it. Yeah, should be first one in the dictionary. Else S for X in range I minus N, comma I. Plus, this is long. We need to break this down to understand what's going on. If X is less than the length of the sentence, for else S for X in range I plus 1, comma I plus N plus 1. Okay, there's a lot going on here. Let's see if we can break it down. Let's create an imaginary sentence. And so imagine our sentence will need to be something like 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we have an imaginary sentence. Let's say for I in enumerate sentence. Let's attack the first part first. See what's happening there. So let's start with what left was equals to our sentence, and we say X if X is greater than or equals to 0, else S for X in range. Pick the particular word is N and minus 1. Oh, I think I see what's happening here. It's better to unroll the comprehension. So I'm going to start like this. For X in range, start by for I in enumerate sentence, for X in range I minus this N, that's window size, comma I, that's exactly before M. If X is greater than or equals to 0, then let's create a list. Let's create something here. I'm going to call it those words. Just
I think I in enumerate sentence is going to give you a tuple.
it's going to be the what?
It's going to give you a tuple. Shouldn't be like I, comma, word or something.
Are you sure? In enumerate sentence?
Yes,
I'm not sure.
he's right. Enumerate will give you index item.
Okay. I understand what you mean now. Oh, in that case,
Just put,
okay. I, comma, word, really.
yep.
Okay, yeah. Thanks, Odun. That was a nice catch. We'll have errored out. So for I, comma, word in enumerate sentence, we are unrolling. So if X is greater than or equals to 0, let's print X is greater than 0. I think I see what's happening here, Sha. Now I see it. Before it was confusing. X. Let's put an F there. Else. Okay. Just close this bash. Else S. Print S. Let's run this and see what we have first. N is not defined. Oh, let's choose N as window size 2. So what do we have? We have S, X is greater than 0, and then we just continue. So yeah, so it looks like what is happening is that this first part of this, there's this first part which you unrolled. is getting windows to the, should I say context words to the left. And that will mean that this second part is to get context words to the right, I believe. And any indexes that are outside of 0 or the length of the sentence, for those particular indexes, we return S. And what's S again? I think I showed you before. S is that starting token. This particular starting token is our S for this particular. So this must mean that that here we're getting our context words. So these two are getting as context words, and let me run it again. This time I'll run everything together just so we can see what it gives us. I'll preserve this output. I'll say post was equals to sentence X, sentence X. Let's pick sentence, and let's pick N is 2. 2 here. What's this? Expected indented block. Sorry to. Okay, that's what we have. Post words. We have. This makes no sense. Let me see. I expected to get a list of tuples. At least that's what I thought would happen. Do you have any idea?
I'm still taking a look.
Oh, okay. I think I understand. What's my value for I? Okay. My value for I was 10. Sorry. Sentence number, what was that number 10? Number 10 was 20. Let's put sentence again, 20. Oh, the context was 16, 18, 0, 0. There's nobody to the right of it. Okay, so it looks like it returned the context words for only number 20. Because if you remember, this particular operation occurs in a loop. On the left, you can see it's in for I, word in enumerate sentence. So in my own particular case, I had run this loop up to 10. So what happened was
The return just the last one.
yeah, it returned I was at I is equal to 10. So for I is equal to 10, it returned only the context for I think at position number 10 in my sentence I had put 20. So if you look at context words for 20, you can only have 18 and 16. Can you see it? And since there's nothing to occur to the right of number 20, it will replace it by S twice. So we have S and S. And in our case, our S is our start token. And our start token is at position 0 in our vocabulary. Does everybody understand that?
Yeah, that makes sense.
Okay. So I think we can just like write the rest and let it run. Now that we sort of understand what's going on there. I think I can delete this guy safely, and I can delete this guy safely. Then we can proceed. And then, so they create a tensor for these are words. For this context was create the tensor, and we say touch the tensor. I keep making mistakes today. Pass in the positive words, and then convert it to the type we created it earlier. And then, so let me just shift down so it's clearer. Then now we have our negative words, which all negative words, then I times K times 2 times N up to I plus 1 times K times 2 times N. Okay, so we have a smaller sample of negative words to use. Then move these guys into a tensor. Touch dot tensor. Negative words and just passing the type once again. Cast it to a particular type. And then let's have our target word tensor. So target word tensor was equals to touch dot tensor, passing the particular word we're learning embeddings for. and then convert it to that same type. Okay, so we have a note here. It says, technically, one should ensure negative words don't contain the context, but it's very unlikely, so we can ignore that. Okay. I think we can just proceed with their own assumption then. So they do a forward pass twice. This is what I was mentioning to Odun before, that I thought they would average it, but what they did is they went over it twice. So in the first case, they pass in the target word tensor, and they pass in the positive word tensor. Yes. Then they calculate a second loss in this case, where they say they pass in target word tensor again. They pass in negative word tensor, but this time they tell it that, we are performing negative sampling. So we have negative sample is equals to true. Now, if you go back to our model here, if you remember in the forward pass of the model, there is a parameter that says negative sample is equal to true. And whenever that parameter is passed as true, we see that the score of the model gets inverted. Sorry, the calculated score gets inverted. And the calculated score is a product of matrix multiplication of the embedding context and the particular word that has been embedded. So what happens here is, in the case where we're doing negative sampling, after taking the matrix multiplication, we get a score, we invert it. So I'm guessing this helps the model learn that these aren't proper context words by inverting the score here. In the case where we're not doing negative sampling, that's you just match it to your positive words. So the score is not at all inverted, and the model can just simply proceed to pass it through its activation function and return, the final score. So that's what I was mentioning to do before. So once we have this, append the sum of these two individual losses. And lastly, return such.start losses the sum of it. Am I making any mistakes? I hope not. Okay. So now to actually train our model, let me just copy this entirety. And stop here. So as usual, we defined our model. After we defined our data set first. After that, we defined our model. After that, we defined an optimizer. Then we defined our loss function, which we just reviewed. And so all that's left now is just like combine everything into a training loop, and then we should have proper embeddings that we can examine together. Okay, so we have imported random and import time also. More time. Anybody wants to be imported? No. Oh, can you imagine? Okay, optimizer. I defined an optimizer already. Oh, can you imagine? Okay. I didn't import math before. So just import math. And okay, so everything looks good. Just delete this guy for now. So let's look through this training code. We have, first of all, they've set a maximum length to be 100. And then they say, for eta in the 100, say, okay, print start, shuffle train. So we shuffle the train data, initialize the words and losses to 0, number of words trained and losses to 0. And we start a training clock. And we put the model to, what's it called? We put the model in train mode from eval. And from then on, we have for each sentence, for an ID, sentence, we're enumerating the train once again, calculate my loss and append the value of my loss once again. And then train was equals to train plus or equals length sentence. Okay. So we add the length of that particular sentence. So that's each time it has seen the word. Then we zero the grad, we zero the optimizer, compute our loss backward. Then we take an optimizer step. And then we have a bit of logging here. Whenever we've trained up to about 50 words, a word divides, number of words divides by 50, I think. And then the perplexity. Interesting. The calculation of perplexity. I should look at this later again. All right, so let's run this and see what we have. Let's hope we don't run into any errors. Note. This is n. I defined all the constants somewhere now. Anyway, just copy it and paste. N was 2, K was 3. And I remember running them. So where are they? Okay. That's fast. So we can actually see perplexity reducing as the model trains. I think we discussed perplexity a few weeks ago. Does anybody have an intuition about it they can share?
No.
Hello? So I tried to find a counterfactual, what's it called? I tried to find a version of skipgram that did not use this negative sampling, but rather just use a softmax straight, so that we could see the difference between these two different models. That's when you use when you use this efficiency trick and when you do not. But I couldn't find anything online, to do that for us. But in the case where we don't use negative sampling, I imagine that there will be none of this what's it called? This is all that will change. There'll be no negative words. All that will happen is I think we would pass it over, instead of this positive word tensor, we would pass it over a list of a tensor that contains our entire dictionary. And then I think what the model would need to do would then be to output the highest probability for the ones that are the context, and the rest you get low probabilities.
Yeah, I mean, it's really expensive because for each word you pick, right? So if you pick a particular word and then you have maybe 2 context words left and right, that's 4. So for each of those 4, you have to do a softmax over the entire vocabulary. So if for each word you are doing 4 softmax over the entire vocabulary, and then you have to do that for all the words, it just takes
in each sentence, in each line in your training data. So It does really get really expensive, especially with very large training data. Okay. So it looks like this might actually take a bit to run. How large is this data anyway? I didn't check at all. But yeah, I think we should hear from others. Any thoughts, any questions, anything that became clearer by stepping through the code together, things like that. Can we share? Or any points you require further clarification on?
I don't have question, but I will go through it after. If I have question, I will ask in the chat.
Oh, okay.
Slack, yeah.
Let's hear from you now, Benjamin. Can you, anything, just share? Somebody sent a message. Oh, okay, okay. So Benjamin said he has another meeting and has to leave. All right. Well, it was great to have you, Benjamin. Join us again, same time next week. David, hello.
Hello. Hello.
Okay. Yeah, so I thought you could share anything you learned, really, or any questions, just general comment on the.
Okay. It's my first time actually. I'm gonna follow you when I'm taking the course study in NLP. Then, if I have a question, I'm gonna share on the Slack. Thank you for your guidance and support.
Okay. All right. We'd love to have you again next week.
Yeah.
I think I sent you the Notion page already.
Okay.
So you should see the course. You should see the topic that we are covering for next week. I'm not sure
Okay.
what it is again,
Okay.
but it's something interesting definitely. So what we do is we individually we go through the course video for the week. It's hosted on YouTube. It's usually about between 30 minutes to an hour. Sometimes they're recommended reading, but more often than not, I know we're all busy folks and cannot get you the recommended reading. But what we do is we individually go through the videos and take notes, and then gather here on Mondays to either discuss things in which everybody can share, or we do a code walkthrough like today. Usually if you're doing a code walkthrough, somebody will do it. Maybe not me, might be Odun or Shamsuddin, or maybe yourself sometime. Yeah, and that's just generally it.
Okay. Okay. Thank you.
All right then.
All right.
David. Ayodele, how are you doing?
Yeah, thank you very much. I'm fine, Akintunde. And thanks for the walkthrough.
It's all right. It's all right. Yeah, so did you have any questions, any thoughts at all? Did it, I think you were here when we did efficiency tricks, right?
No, I wasn't. I think I missed that class. Or I came late or something. Yeah, I think it was the day I came late, yeah.
Oh, okay, okay. All right, but, okay. All right then. All right.
But no problems. I think I understood what we walked through today, but I need to sit down and do some codings myself, especially some things that I've not gotten their rudiments, so I can flow along.
All right then.
In subsequent classes.
Okay. As usual, if you have any questions, please you can raise it on the Slack page. I'm definitely sure there'll be somebody to share maybe something that's helped them develop a better intuition in the past, or a resource that can help, and it will help others also. So
okay,
study group. All right then. Shamsuddin.
Thank you, Tunde. Thank you.
Yes. All right, thanks, Odun, for the resource. Was there anything else I was going to share? Yeah, so for next week, I think we are going to be looking at recurrent neural networks. And under recurrent neural networks, they're going to mention LSTMs. So I wanted to share one of the best resources for LSTMs. Everybody, which I found. Colas get this really very well visualized to help you develop an intuition for LSTMs. So I'll see you guys next week.
Sorry, before you go, quick one.
Sure.
Yeah, so ideally, right, what we're trying to do here is we're trying to learn embeddings for words, and the assumption is the weight of the model is the embedding, right?
If I'm right, it's usually the, how do I call it?
Yeah, look at line 157.
Last layer. Line what?
157.
Okay.
Yeah, so it's the weights that are the embedding, right? So my question before was, we have word embeddings and then we have like the context embeddings. And the length of both the word embedding and the context embedding is the length of the vocabulary, which means basically we're trying to learn two representations for the words. One for the word as the center word and the other one for the word as the context word.
Yes. Yes.
Yeah. So the reason why I asked that question earlier was, if you look at line 157, this
Yeah.
tutorial is just using the word embedding as the embedding, and
Yeah.
are completely doing away with the context embedding.
The context, yeah.
So my question before was, don't you think it is ideal to just like add two of them together for each word and maybe take an average?
And get like a better representation for each word that way.
Yeah.
Okay. So I've heard what you said mentioned before. What I don't know is what is ideal. But I remember that in some cases, I've heard cases where they averaged both embeddings to get better representations for a particular word. What is ideal or like not ideal? I do not know. I imagine that there's been papers that look into which work better.
Yeah.
And I imagine that there might be different tasks for which different embeddings might work best. So I think maybe it's just this tutorial that just decides to pick this particular one. I know for some cases I've seen them averaged before. So I think task could play a role. What type of task are you doing? Let me see if I can find anything. Averaging word and context. Embedding what to pick.
Maybe just so we don't take too much time. I guess me and you can discuss this out of here.
Oh, okay. All right. Oh, it's already past 8. All right. Shamsuddin, did you have anything you wanted to share before we close out?
No, it's okay.
All right then. All right, guys. Thank you all for joining. And sorry we've taken longer than we planned. And see you guys next week. And as usual, the Slack is always open.
Thank you.
Okay.
Thank you.
Okay, thank you.
All right. Thank you guys for joining.
Thank you.